So these are the simple Boolean expressions that all this is you've done in Math 1, it's simple linear algebra. And then these are some of the expressions you'll use, I mean, commutative, associative. The key expressions that you need, which will be used most of all, would essentially be De Morgan, absorption, and consensus, right? So these three are not typically, so the rest of them you've done in algebra, so it's not something which you're seeing for the first time. Just these three are the most important things which you probably may not have done in algebra before, so this is good to keep in mind when you're dealing with Boolean functions, okay? And then the other thing you want to think about is De Morgan's theorem that which we looked at for two variables can be extended if you use induction. You can prove it for yourself that you can extend this to multiple. So always remember that inversion of an OR function gives you an AND of the inverted functions, right? So, or you can say, so if I do an OR first and then invert, it is equivalent to inverting first and then ANDing, right? So this is important because suppose I want to implement this function, I can either implement the function as doing all the OR gates first and then doing a final inversion at the end, or I can do the other way around where I invert all the inputs and then send them through an AND function. And the dual of that would be AND invert is equivalent to invert OR, right? So if you're going to move the invert from after to before, then you need to flip the OR to AND, right? So this is important to keep in mind because this will what you'll be using a lot when you're going to implement these functions at the gate level, right? So always remember that OR invert is invert AND 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 invert is invert OR. It'll come up in handy much later when we start converting to different gates. When we move from implementation from an AND OR to an AND or NOR, these things come a lot into, it does help you a lot there. And the other thing, which is pretty, it's something which is easy to think about, is that if I think about a function which is made up of n variables, right, then I can think about it, I can pull one of the variables out. I can say this is a1 ANDed with the function with a1 spelled as 1, right? So I can evaluate this function. So I can evaluate this function as 1 f1 where I've evaluated with f with a1 equal to 1. And I can evaluate an f0 function which is f with a1 equal to 0. So I can define this function as a1 ANDed with f of 1 plus a1 prime ANDed at f of 0, right? So what does it mean? This means that when a1 is true, a1 prime is false. So the other way to think about 0 and 1 in regular logic is we call this true and we call this false, right? So if I'm going to talk in Boolean terms, I can say that the function value of this n variable function, if a1 is true, that is if a1 is 1, then a1 prime is 0, so this drops off. And if a1 is true, then we know that a1 is 1, so the value of f becomes f1. And when a1 is false, that is when a1 prime is 1 and a1 is 0, then the function drops down to f0. So it's trivial when you think about it, but it's again powerful when you have to design this at a circuit level, because say some inputs you'll be able, so as we go through the class, I'll give you examples where this becomes very easy to design circuits, right? So these are just quick tricks to keep in mind when you have to actually implement this on a breadboard. So now let's look at, just clarify something. So let's quickly take a minute. Suppose I tell you what is the dual of this function, right? So what do you do for a dual? Always remember, for a dual, you have to convert all the ORs to AND and the ANDs to OR, right? You don't touch the complements, right? So if I have to ask you, find the dual of this function, convert this to an and there is an AND here, convert that to an OR. So what you get is that the dual function of f is given by a ANDed with b prime or c, right? So this is going to be the dual of the function. So any function, to get the dual, again, convert all the OR functions to the AND function, right? And convert all the AND functions to the OR function, right? And the other important thing you need to keep in mind is how to find the complements. So if I've given you f as this, take a second and find out what f prime is. So how do you write f prime? So f prime is given by a plus b prime c, the whole prime. Use De Morgan's theorem. It is OR invert. OR invert becomes invert AND. So it becomes a prime ANDed with b prime c prime, the whole prime. Now b prime c prime, now again apply De Morgan once more. So it becomes a prime. This is AND invert becomes invert OR. So it goes to b plus c prime, right? So f, if it's a plus b prime c, then f prime is given by a prime ANDed with b plus c prime. So again, this was a simple case where you just had two terms, but this is something again which you'll have to do pretty commonly. And why is that important? Because sometimes what happens is, so right now we have been paying a lot of attention to f and f prime, right? And we treat f and f prime as essentially independent functions. But what you'll see is as we start doing more and more design, I always, if I know the value of f, by definition, I know the value of f prime. I can generate f prime, right? Just passing it through an inverter. And similarly, if I know f prime, I know what f is, because f and f prime are just complements of each other. So sometimes what happens is you'll see, and again, take my word for now, but you'll see more examples later in the class, that sometimes you'll find that if I have to implement f, I might need 10 gates. Whereas if I'm smart about the implementation, if I use f prime, I might end up taking only 8 gates or something. So what happens is many a times this becomes very powerful when you want to minimize the number of gates, right? And why do you want to minimize the number of gates? You want to minimize the number of gates, one, because hardware is less, right? So debug is easy. So this, if you were in if you were running this class on campus, unfortunately, you would have understood this the hard way, simply because when you go to the lab, you realize any extra gate you would want to implement in your design in the lab, it becomes that much harder to debug when the system doesn't work, right? So minimizing is always a good idea, because that helps you reduce the headache of debugging. And the second thing, obviously, is lower power, speed high. So these are all your standard reasons why you want to minimize gates. But primarily in this class, if you are doing a lab, and if you, so even when you do the design assignment later, right? Remember, it's very important when you do design that keep your number of gates, keep the amount of hardware you need to as low as possible. Do not add hardware unless absolutely essential, right? So, and here's the trick. Here is what makes a good digital design engineer, is somebody who can get the same function done with the least amount of hardware, right? And so always remember that all our, and we'll spend the next few lectures stressing this. We will find different ways of minimizing Boolean expressions and looking at circuits which can effectively implement the same function with less number of gates, right? So now let's do this. So take a minute. So I'm giving you, and these are kind of questions that we'll work a lot over the next few weeks. So I've given you this expression. So if nothing is specified, right, then you assume that this is a function of x, y, and z. So I've given you this function. Try and simplify. So what do you want to do? When I say simplify, means you want to reduce the number of terms, and you want to reduce the number of variables, right? That is, you want to ensure that you have less number of x, y, and z available, less number of x primes, etc. available, right? So take 2 minutes and figure out what the answer for this is. So ideally, you go by collecting terms. Collect the terms, simplify. And why is that? So you can collect terms, right? If I collect x prime and z from this and this, so I can write this as f as x prime z times y prime plus y. So I've collected this, and then I collect these two terms. When I collect these two terms, I get xz times y plus y prime, right? And you know y prime plus y is, this is 1 and this is 1. So what you get is x prime z plus xz, which is nothing but z times x plus x prime, which is z, right? So this function is essentially just the value z. What this means is that if you think about implementing this function, and this is your output, let's not call it output, let's call this output. So this output is essentially just transmitting the z input. X and y inputs are not necessary for your function. So even though you're collecting these inputs, they are not important for implementation, right? So like, why is this important? So going on, right, then you'll ensure that all your information coming in Z becomes very critical to performance of the system. So you will not spend a lot of time optimizing X and Y. You'll spend a lot of time ensuring that your signal Z is true to the information that you want to process, right? And this is a very simple case, but generally that's what happens. Again, these minimizations help you figure out which is the key term which is important. So that will tell you, okay, which signal is important for me, and ensure that I spend enough energy in ensuring that that signal is tracking information, right? The other way to think about this would have been, I collect all these terms, right? And what you see here, and we'll do this. So again, when you another week, and you quickly see that this is all the possible combinations of x and y. That is, this term will be 1 for any combination of x and y. So for example, when x is 0, this term drops off, this term drops off, right? And these two terms remain, and these two terms will always add up to 1, because when x is 0, this becomes a 1, this is y prime, this becomes y plus y prime stays 1, so this term becomes a 1. Similarly, you see that when y is 0, these terms don't drop. So what you'll see is that this sum is always 1. For any combination of x and y, this sum is always 1. And so basically what you get is f is z. And this is very, so again, when we finish a few more lectures in the class, you'll be easily able to identify what this is. And you'll see that this is always going to be 1, which means that f is always going to be z, right? So given any Boolean expression, you should be able to minimize it using the Boolean Boolean laws that we've just went through, Boolean theorems. We'll also look at a simplified method. So this is the cumbersome method of doing this. Then what we'll look at is, in 2 lectures, is this method known as K-maps or Karnaugh maps. And Karnaugh maps are a very powerful graphical method to do the same thing. And you'll see like with this, it's only a matter of seconds before you can minimize any function, right? So again, we'll teach all this in class going forward. Okay, so a note on Boolean functions. So one way to think about a Boolean function is as a combination of AND or invert, right? I can express a Boolean function as a Boolean expression made up of all the inputs that I have for the function. The other way to think about how to express a Boolean function is known as a truth table. So a truth table is very simply just for all the different way combinations of input, what does the output look like? So now, quick question. Suppose I have 3 inputs. If I have 3 inputs, how many input combinations can I have? And if one of you can open your mic and answer. Suppose I have a 3 input function. How many input combinations can I have? 8. 8, correct. Why is that? Because it's 2 cube, right? Because every input can be a 0 or 1. So for 3 inputs, I can have up to 8 combinations of my inputs, right? All from 0, 0, 0 all the way to 1, 1, 1, right? And this can be termed as 0 to 7, right? So if I have 3 inputs, so I can also think of this as a 3-bit binary number, right? So if I think about a 3-bit binary number, say my input functions are x, y, z, right? So a 3-bit binary number, so how many numbers can it represent all the way from 0 to 7? So if I think about a 4 input using the same logic, I will have 16 combinations of inputs. And so for an n input Boolean expression, I can have up to 2 power n. So remember, why is this important? And again, you'll see that a lot of these hand calculations of these very simple things that you're doing in class are fine when you're dealing with 3 input, 4 input. Now, if I give you like a 20 input Boolean function, you have to do it with 2 power 20 input combinations, which becomes cumbersome. And so obviously there are a lot of recursive software available which can do this much easier. But what in this class, what we do is quickly go over 3 input, 4 input, up to 5 input, and figure out how to do minimization for those expressions. So how do I do a truth table? Now suppose I have this function, right, which is, it's a function made of 3 inputs, right, and this is my function. So I've asked you, how do you fill the truth table? So again, the truth table is given, you first draw what is known as, so these are your inputs, x, y, and z, and this is my output, right? Now this, again, this is normally I use a serial because this tells me what are the different inputs. So I know it's a 3 input function. So a 3 input function will have 2 to the power 3, so 8 combinations of inputs. And those are nothing but the binary equivalents of these decimal numbers, right? So I go 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Right? So these are all the possible input combinations I can get for this function, right? All the way from the decimal binary equivalent of 0 to the binary equivalent of 7. So what I have to do is, for every input combination, I need to identify what the value of z is going to be, right? So and that gives you essentially the truth table of this function. So why don't you quickly evaluate f for all these various combinations? So let's look at this. When x is 1, this function is going to be 1 no matter what y and z are, right? No matter what y and z are, if x is 1, this function is going to be 1. So for values from 4 to 7, right, these values, x is always 1. So no matter what y and z are, f is always going to have the value 1. Now when x is 0, when does the function have a value 1, right? So the function will have a value 1 only when y is 0 and z is 1. So only when y is 0 and z is 1 will this function have a value 1, right? So only when y is 0, z is 1, this function has the value 1. For all other values or input combinations, this function will have the value 0. And so this is the truth table of this function. So I could have given you either this expression, or I could have given you this truth table. It means the same, right? So what we'll see is how to convert something from this truth table back to this function, because this is important, because this tells you how to connect your gates, right? So if I want to implement this as a circuit, how would I do? I would take x, right? And first I need to find out y prime and z. So suppose this is x, so I'll take y, invert it to get y prime. Then I'll take z, I'll add the two together to get y prime z. Then I would take x and y, the AND of those two, or them, and get my output, right? So this is your y prime, this is your y prime z, and this is your function, right? Again, let's trace it. I want to implement this in a gate level. So I know x, y, z are my inputs. So if x, y, z are my input, I need to first generate y prime. So once I generate y prime, which is done by passing y through an inverter, now I can take y prime and z, send it through a 2-input AND gate. So the output of that AND gate is my AND function y prime z. And I need to OR that to x. So I take the output of the AND gate and send it to the input of an OR gate, which also has an x coming in, and so finally I get the function, right? So if I want to implement any function, I need to get it to this stage, the minimized Boolean expression, right? And so truth table is one way by which you can give, so the function can be expressed either as a truth table or as an Boolean algebraic function. And both essentially mean the same thing. What we figure out is, suppose a truth table is given, how do I get it converted here? Or this one is very easy. Converting from a Boolean expression truth table is very easy. All you have to do is find out how many input combinations exist, and then find the value of the function at every input combination. So an easy way to remember this, and this is sometimes used, it's up to you if you want to use it or not, is that, remember, what am I treating? This is my MSB. This is my LSB. right? When I code it as 0, 1, 2, 3, 4, 5, 6, 7, right? My X is going to be my MSB, my Z is going to be my LSB. So when I do that, my LSB flips every row, right? So it goes 0, 1, 0, 1, 0, 1, 0, 1. My Y flips every 2 power 1. So it's going to go 0, 0, 1, 1, 0, 0, 1, 1. The next bit is going to flip every 2 squared, every 4. So it goes 0, 0, 0, 0, 1, 1, 1, 1. So if I had like a 4 input function, right, this would go 0, 0, 0, 0, 1, 1, 1, 1 and repeat itself again. And then I'll have suppose I had a W function, that W function will be 0 for the first 8 entries and then be 1 for the remaining 8 entries, right? So if I want to think about this, I can also think about the input functions like this. And again, this becomes useful when you're designing, is that I can say, okay, my Z, so how does my Z look, right? So I can think about it like this. So I can think about it as various pulses. So Z, for example, stays 0, then goes 1, 0, 1, 0, 1. So in voltage, this is how it looks like. So 0, 1, 0, 1, 0, 1. I have 8 values and goes back to 0. Now, if I think about Y, so this is your LSB, right? If I think about Y stays 0 for the first 2, then goes 1 for the first next 2, then goes this. Now, if I think of X, which is your MSB, now Z is going to go. So if I look at every, so this is sometimes known as what is known as a timing diagram. So I can think of my inputs for a 3-input function. So again, this is T0, T1, all the way up to T7, right? So if I generate, so you can think about it. Suppose I generate 3 pulses, one with a frequency of say F. What is the frequency of this? What is the frequency of Y? If the frequency of Z is Z is F, what is the frequency of Y? You can unmute and speak. F by 2, right? Or F by 2 power 1. Frequency of X goes F by 2 power 2. So as I have more and more variables, as I move from the LSB towards the MSB, I'll see that its frequency drops down. So if I want to generate all 8 combinations, right, all I can do is generate 3 pulse trains, one which has a frequency F, one which has a frequency 2, F by 2, one which has a frequency F by 4, and I can get all the 8 combinations. Now, why is this important? Because now if I look at the value, now if I want to plot F here, right? So what does F look like? If you go back to the previous slide, F looked like 0 for the first, 1 in the second case, and then 1 for 4, 5, 6, 7, right? So if I want to plot F on this graph, what I would do is, I would say it was 0, went high in the second instant, went 0 down all the way, and then was high whenever X was 1, right? So this was your value of F. So I can think of the same truth table. Now I've shown it as a timing diagram. Now for the timing diagram, again, I'm ensuring that my X, Y, and Z are able to generate all the 8 input combinations. So if I can generate that, then I know my F should look like this, right? Which I'm basically saying that F is high. So I can also think about, if I want to write it like this, I can say F is high when input word is 1 and 4, 5, 6, 7, right? So I'm saying is F is high. So again, what am I calling the input word? The input word is made up of a number with X, Y, Z, where Z is my LSB and X is my MSB. So I can think of it as an input word. It's a 3-bit word. And I can say that my input is high, F is high, only when the input word has 1, 4, 5, 6, 7. And for all other values, so the other values are what? The other values are 0, 2, 3, right? So for 2, 3, F is 0. So other way to think about this, and why is this important, we'll talk about later. So you can think about a function in multiple ways, right? You can think about it very simply as a Boolean expression. You can think of it as a truth table. You can think of it as a timing diagram, or you can think of it as a mapping of the input word to an output. Okay, so so a couple of terms to keep in mind before we go forward. So again, why are we doing all this? We're doing all this because we want to ultimately implement this at a gate level, right? So when a Boolean expression is implemented in the logic gate, each term in that expression, you'll have to implement it on a gate, right? So in the previous case, when you had x plus y prime z, that plus was interpreted in a gate and the y prime z was implemented in a gate. Now, we'll call something known as a literal, and literal is a single variable within the term which is complemented or uncomplemented, right? For example, if I say a term, if I call a term y prime z, y prime z is a term which has two literals, a y prime and a z. X is a term which has only one literal because it just has the value x, right? There are no other forms of variables available. If I had something like this, a term like xyz, xyz is a term which has three literals, right? And why is this important? Because suppose I'm in the lab and in our lab, suppose I have only two input gates, right? Suppose I'm working in a lab which has only two input gates. That is, I cannot implement this function in one gate. I need to use two gates to implement this function, right? So when I have something like two input gates, then it's important to reduce everything down to two literals, right? Because that's the only way you can implement it in a two input gate, right? So again, this is just a technical term for when you look at a term and say literal. A literal basically means, so a term like this would also have two literals. A term like this would also have two literals. As long as it's either in its complemented or uncomplemented form, as long as it's a variable, then it will have two literals, right? So again, as I mentioned, we want to implement the function in its simplest form. So all this thing we're doing just to ensure that we're able to get the function down to its simplest form, which means it has less number of terms, less number of literals per term. So that will ensure that we have less number of gates in our design. And as I mentioned, we'll sometimes keep this in mind that it's not necessary that you have to, and especially when you start doing labs, when you start doing labs, this will become very apparent that you may not necessarily have to implement F. Sometimes implementing F bar will give you a much elegant solution, and all you do is at the end of the F bar implementation, stick it through an inverter, and you'll get the value of F. So again, when you start doing things in lab, you realize this, that it sometimes becomes easier to implement the F prime function than the F function. Again, this is your goal. At all times, this is the goal that you have in this class. You have to always ensure you have as low the number of gates as possible. So sometimes I'll throw in roadblocks for you saying that, okay, implement this only using NAND gates. You cannot use AND and OR. So I will tell you that implement something like this. Or I'll say only use two input gates. And the reason may not be apparent to you right now, but as you do more and more electronics in the class, you realize why some of these forms are important, because ultimately it ends up being that this is the only way you can implement it in a microelectronic circuit. So if nothing is specified to you, obviously I can do something. So I can design a gate. I can do this design, which is implement. What is this gate implementing? Gate is implementing the function, right? It's a 4-input AND gate implementing an AND of all the 4 inputs. Now, what you again in this class, I don't have the you don't have the background to understand this, but what you see is that a gate like this would be a bad implementation in electronic design, because this gate will be much slower than a 2-input gate. So sometimes as you start looking at 6-input, 7-input AND gates, they don't make sense. So what you'll do is you'll rather implement this something like this. So I'll implement it as 3 AND gates, right? Which basically do 3 2-input AND gates, right? And you'll see that these kind of designs, Again, this is a very simple example and it may not hold true here, but you'll see that as you start implementing like 7 input, 8 input functions, you'll sometimes find that implementing it in a single gate will be cumbersome and will cause the gate to be a very slow gate. And sometimes it would just be beneficial to implement it as two-level implementation, which will give you a much faster circuit. Again, this is something which you will not be able to appreciate it in this class, but in later advanced classes, you can understand why that's the case.
So,
Yeah.
so if we have something like x plus y into z, then how many literals does that have?
When I have something like x plus y, the whole thing into z or just?
No, just y into z.
Huh. So what I'll say is this term has one literal, this term has two literals, so there are three literals present in this expression and two terms. Right?
Okay, so we separate the terms using OR gate.
Right. So generally when we say terms are normally, so we'll talk about these things. For now, just remember it as separated by OR, but we'll talk about two kinds of terms, a min term and a max term. And I'm just coming to that. So in this case, this is a min term because it's implemented as an AND gate. You can also think of this as if you're taking the complement of this, right? Then this would be x prime tron y plus, right? This would be your implementation of the complement. Here, what we'll call is this will be a max term. So again, we'll talk about this. Don't worry about it. For now, when you think of an expression like this, you can say that this is three literals with two terms. Even here, it's three literals and two terms because the two terms are x prime and y prime plus z prime, and the three literals are x prime, y prime, and z prime, right? And that is implementing your f prime function. So again, number of literals always goes as the. So suppose I had a function which did this. Suppose I had xy prime plus x prime yz. Suppose this is my expression, right? In this case, how many literals do I have? In this case, I have more than three literals because I have x and x prime, right? So in this case, you can talk about literals. So in the strictest term, I will say that the number of literals are 5 because x and x prime are different literals. Or if, and this is again, this is driven by whether you have, so many times when you do digital design, right? You will see that we won't care whether it's x or x prime because whenever we generate signals, we'll always generate the complement of it at all times. So a good designer always generates complements. But in this class, again, we don't have that requirement. So I can say that this still has three literals only because x and x prime, I club it into a single literal because I want to implement it as a NOT gate, right? So this definition of literal and term and all is very flexible. So don't worry too much about it. What you want to remember is that it is going to tell you how many of those terms are how many of those inputs are actually valid, right? Suppose you want to, so you want to reduce the number of inputs which are essential for you, right? So all you're doing here is removing the unessential stuff in your expression. So you want to get to the basic minimum number of terms which are needed to implement your gate. So all that you have to do is ensure that the number of literals are less, number of terms are less, right? Keep going down till you know you cannot go lower than this. Now, when you do something using Boolean functions, you'll see that it's hard to figure out whether have you gotten to the minimum term or not. When we do K-maps, you'll see that it's very easy with K-maps to figure out whether I've gotten it to the most simplest form or maybe I have some way to go further. So when we do K-maps, you'll realize that will get you to the simplest form much easier. Doing this using this Boolean word is kind of rudimentary. That's not your ultimate expectation. I have from you is using K-maps and get it down to the simplest term. Okay, so then we talk about, again, these are technical terms, what is known as a canonical form and a standard form. So answer, suppose I have two binary variables. How many possible combinations can I have in an AND operation? Right? So you can think about it. Suppose I have two variables, x and y. Right? So I have 0, 0. So I'm forming the truth table now. So again, if I call this MSB and LSB, again, you don't need to do it every time, but I'm just reinforcing it. So if I call this a word, then I can call this 0, 1, 2, 3. So I have four combinations of input, right? And if I look at the AND gate, right, the AND gate here is going to give me an input of, so this is my implementation of an AND gate, right? Now, Suppose I want to, so let's do this instead, that I have these four values. Now I'm going to ask you a different question. So I want to implement four functions with the following truth table. So I want to implement four functions, right, which have the following truth table. That is, f0 is high only when x and y are both 0. f1 is high only when x is 0 and y is 1. f2 is high again when x is 1, y is 0, and f3 is high when both are high. So what can you tell me the expression for f0 is? One of you? Suppose I want the Boolean expression for x0. What is it?
X prime, Y prime.
Correct, right? Because x prime y prime is the only when x and y are both 0 will this function go to 1. For all other input combinations, this function remains a 0, right? If I think of f1, what is the Boolean expression for f1?
X prime y.
Correct. And similarly, I can think of f2 as xy prime and f3 as xy. And how do you do that? Remember, if there is a 0, prime it. If there is a 1, leave it unprimed, right? So here I immediately see x prime y prime, x prime y, xy prime, and xy, right? So what I've done is I have these four terms, right, which is nothing but x prime y prime, x prime y, xy prime, and xy. These are the four and combinations of these two binary variables, right? So the two binary variables, I can either do AND of just xy or prime one, leave the other unprimed, right? So I can create four AND gates, which is what I've done using these functions f0, f1, f2, f3, right? So these four terms are the four possible combinations of a two input AND function, right? And these terms are nice because these terms go high only at one particular combination of the input, right? So the advantage of these functions f0, f1, f2, f3 is that that function goes high only when that particular input combination is selected. It is f0 goes high only when xy is equal to 0, 0. f1 goes high only when xy is 0, 1. f2 goes high only when xy is 1, 0. And f3 goes high only when xy is 1, 1, right? So these four AND terms are known as what are known as min terms, right? In logic design, these are known as min terms of standard products. So for a two input gate, for a two input system, these are known as a standard product. Why standard product? Because these will go high only at one instant for that given input expression, right? And sometimes the convention generally uses small m and the subscript, right? So for example, this m0 is nothing but f0 in our expression, right? So m0 means, suppose I'm talking about the two input function, then m0 means, so if I say f is equal to m0, right, it means that f is 1 only when input is 0, 0, right? So I can, so if I have four variables, if I have two variables, then I have four standard products, which are m0, m1, m2, and m3, right? So this same f0, f1, f2, f3, I'm just renaming it as m0, m1, m2, and 3, right? Suppose I had three input variables, then how many minterms will I have? Anybody?
8.
8, right? And again, all those 8 terms can be expressed as a Boolean expression, right? So suppose I had suppose I had three inputs x, y, z, right? Which means that I can have 8 combinations all the way from 0, 0, 0 to 1, 1, 1. Again, look, we are just looking at a different way of the truth table. So there's nothing complicated what I'm doing here. I'm just calling different ways of looking at the truth table, right? So if I think about x, y, z, I can have 8 input combinations. And so when I look at minterms, I will talk about minterms m0 to m7, right? And what does M7 mean? M7 will be given by the expression XYZ. M0 will be given by the expression X prime, Y prime, Z prime, right? So each of this minterm means that the minterm goes to 1 only for that input binary combination, right?